In a parking lot outside a laboratory in Irvine, California, in April of 2026, a machine the size of a shipping container was switched on for the first time in front of cameras. It had no well beneath it, no pipe running to it, no reverse osmosis membrane inside it. By the end of that day, it had pulled 4,000 liters of clean drinking water directly out of the air. The man who invented the chemistry behind it had received a phone call from Stockholm 6 months earlier. He had just won the Nobel Prize. And starting this year, for the first time ever, you can actually order one. Let's find out how a crystal, smaller than a grain of salt, became one of the most important American inventions of the decade, and why, even with a Nobel Prize behind it, you still cannot buy one for your own backyard. Here is the number that started this entire race. The United States Geological Survey has measured how much water is floating in Earth's atmosphere at any single moment. The figure comes out to roughly 12,900 cubic kilometers. Now compare that to every river on the planet combined. The Amazon, the Mississippi, the Nile, the Yangtze, all moving at once, add up to about 2,100 cubic kilometers. There is nearly 6 times more water hanging invisibly over your head right now than there is flowing through every river system on Earth combined. It is simply spread so thin, a few grams per cubic meter of air, that for 2 centuries nobody had a cheap way to grab it. That is the exact problem one American chemistry lab spent 19 years solving. The timing could not be more urgent. Data centers built to run artificial intelligence models are already burning through water by the billions of gallons every year for cooling, competing directly with farms and cities in some of the driest parts of the country. Some of these facilities use more water in a single day than a small town uses in a month. Whoever solves cheap water extraction in a desert does not just win a science prize. They solve one of the actual physical bottlenecks standing in the way of the entire AI industry. To understand how strange and personal this story really is, you have to start with the man at the center of it, not the machine. Omar Yaghi was born in Amman, Jordan in 1965, one of 10 children in a family with no running water and no electricity for much of his early childhood. He has said in interviews that his fascination with molecules began as a boy flipping through a chemistry book in a local library because it was one of the only books he could find. At 15, he moved to the United States alone to attend college, eventually earning a doctorate and building his entire scientific career inside American universities. Every major breakthrough that follows in this story, the patents, the papers, the company, happened after that move. This is not just a chemistry story. It is an immigrant scientist story that happens to end with a Nobel Prize and a factory in Southern California. So what actually is the material at the heart of this invention? It is called a metal organic framework, shortened to the letters MOF, and this specific version is named MOF 303. If you have never heard the term, picture a sponge built one molecule at a time. Metal atoms sit at the corners of a repeating structure. Long carbon-based molecules connect those corners like tiny scaffolding struts. What fills the space between them is deliberately almost nothing. That emptiness is the entire invention. You already know materials that pull moisture from the air. Silica gel, the little packets that come inside a new pair of shoes, does the same basic job, and so do the zeolite crystals used in some industrial dehumidifiers. But those older materials were never engineered at the molecular level. Their pores come out, however the chemistry happens to settle. A metal organic framework is different because chemists can choose the exact size, shape, and spacing of every single pore before it is ever built. Under a microscope, MOF 303 looks like an unremarkable white powder, but inside every grain are channels running through the crystal about 6 angstroms wide. An angstrom is 1/10,000,000th of a meter. A single water molecule is roughly 3 angstroms across. In other words, the tunnels inside this powder were built to a tolerance barely wider than the very molecule they are designed to catch, and narrow enough to more or less ignore everything else floating in the air around it. The first working version of this chemistry used a metal called zirconium, which runs about $160 a kilogram. That is a perfectly reasonable price for a laboratory experiment and a completely unreasonable price for a product meant to sit in 10,000 backyards or 100 data centers. So chemists at Berkeley rebuilt the exact same framework around aluminum, instead, the same cheap abundant metal used in soda cans, bringing the cost down to roughly $3 a kilogram. That single substitution, swapping one metal for another while keeping the pore structure intact, is what eventually turned a laboratory curiosity into an actual company. Now here is the part that genuinely makes this invention work, and it is not the surface area, even though that number is almost hard to believe. If you could somehow unfold every internal surface hidden inside just 1 gram of a related framework developed at Northwestern University back in 2012, it would cover roughly 1.5 American football fields. MOF 303 itself is more modest, closer to 1,300 square meters per gram. Still about a quarter of a football field folded into a pinch of powder you could hold between 2 fingers. But raw surface area was never the bottleneck. Plenty of materials have enormous internal surface area and still make terrible water harvesters. What actually makes this material special is the shape of a specific curve chemists call an adsorption isotherm, which simply describes how much of a substance a material holds at each level of humidity. Most desiccant materials load up gradually. As the surrounding air gets a little more humid, they absorb a little more water in a smooth, sloping line. That sounds reasonable until you think through what it actually means in the desert. A material like that never fully loads in genuinely dry air, and it never fully releases its water without serious energy-hungry heat. MOF 303 refuses to behave that way. Below 12% relative humidity, it holds almost nothing at all, practically bone dry. But cross that 12% threshold and the pores fill almost instantly. By the time the surrounding air reaches 20% relative humidity, the crystal is carrying nearly 40% of its own weight in water. That step-shaped curve, sudden and aggressive instead of gentle and gradual, is the entire engineering achievement hiding inside this powder. It is aggressive enough to strip water directly out of air drier than most deserts on Earth ever get. But the bond holding that captured water in place is a weak physical attraction rather than a true chemical bond, which means the crystal lets that water go with nothing more than the mild warmth of morning sunlight. No boiling required, no compressor, no electricity at all, just the ordinary temperature swing between a cold desert night and a hot desert day, a swing that happens for free every single day everywhere on the planet. It helps to follow one single water molecule through an entire cycle to see how elegant this really is. At 2 o'clock in the morning, desert air has cooled, and relative humidity has climbed, and an open cartridge of this powder sits exposed to the night sky. Individual water molecules drift into the microscopic channels and stick to the pore walls. By the time the sun comes up, those pores are fully loaded. The cartridge then seals shut inside an insulated housing. Sunlight heats the powder from outside, and the trapped water lifts off the pore walls as vapor, with nowhere to escape except toward a shaded metal condenser positioned nearby, kept cooler than the powder by a simple reflector blocking direct sunlight. There, in that shade, the vapor turns back into liquid and drips down into a collection tank below. Reset at nightfall, and repeat the exact same cycle again the next day indefinitely, powered by nothing but a sunrise that was already going to happen regardless. The idea behind all of this goes back much further than most people realize. In 1974, an Australian chemist named Richard Robson was preparing a teaching exercise using simple plastic ball and stick molecular models, and found himself wondering what would happen if those same linkages were built at real physical scale as actual crystals containing deliberate, engineered, empty space. That single question was picked up independently years later by a researcher named Susumu Kitagawa, working in Kyoto, Japan, and separately by Omar Yagi, working in the United States. All three of them eventually shared the 2025 Nobel Prize in Chemistry for turning that one question into an entire field. Yagi gave that field a name, reticular chemistry, meaning the deliberate stitching together of small molecular building blocks into large, extended crystal networks with a purpose designed inside them from the very beginning. Yagi's team was not even trying to make water when they stumbled onto this application. Their original goal was capturing carbon dioxide directly out of the air to fight climate change, and they kept running into an infuriating problem. Their frameworks kept grabbing water vapor out of the air before they could ever get to the carbon dioxide molecules they actually wanted, and they were doing it at humidity levels where almost nothing else on Earth could pull water out of the air at all. That inconvenience turned out to be the real discovery. The first actual working prototype device arrived in 2017, built in partnership with engineers at MIT, loaded with the earlier, more expensive zirconium-based framework. 1 year later, the redesigned aluminum version MOF 303 was driven out into the Arizona desert for its very first real-world field test. That passive prototype, carrying no battery, no solar panel, and no moving parts of any kind, pulled 70 grams of liquid water directly out of some of the driest air in the country over one full day and night cycle. Barely a quarter of a cup. But it was proof, sitting right there in the Arizona sand, that American desert air could be turned into American drinking water using nothing but an engineered rock and a sunrise. The science kept improving from there. In July of 2023, Yagi's team published results in the journal Nature Water, describing an upgraded harvester built from stacked layers of the powder, blended with a small amount of graphite to help it hold its shape. Conduct heat evenly with open channels between each layer so air could move freely through the whole stack. Tested in Berkeley, that device produced 285 grams of water per kilogram of material per day. Tested in Death Valley, one of the hottest and driest places on the entire surface of the planet, it produced 210 grams. Both numbers were achieved with absolutely no power input beyond ordinary ambient sunlight, and both results roughly doubled what the earlier passive design had managed. A separate, more aggressive version of the device, published in the journal ACS Central Science back in 2019, used small solar panels to run a fan and a heater, allowing it to complete dozens of absorption cycles every single day instead of just one. That active version reached 1.3 liters of water per kilogram of material per day, a genuinely better number, but no longer a fully passive machine, since it depended on electricity to run its fan and heater. Then, in October of 2025, Omar Yagi's phone rang with a call from Stockholm. He, along with Susumu Kitagawa in Japan and Richard Robson in Australia, had been awarded the Nobel Prize in Chemistry for the invention of metal-organic frameworks as an entire field of chemistry. It was global recognition for a discovery that by that point was already quietly sitting in a startup's parking lot in Orange County, California, waiting to be shown to the world. That startup is called Atoko, founded by Yagi himself back in 2020. In April of 2026, Atoko rolled its shipping container-sized harvester out in front of Bloomberg's cameras for the very first public demonstration. Running on grid power, the machine produces up to 4,000 liters of water a day. Running completely independent off-grid, it still manages over 1,000 liters daily. The water that comes out the other end is close to distilled quality, because the framework is built to grab water molecules, and essentially nothing else. No dissolved salts riding along, no PFAS chemicals, no microplastic particles. And here is the part of this story that makes it about right now today rather than just science history. Atoko has confirmed publicly that it will begin taking its very first customer orders in the second half of 2026. That window is happening right now. The company is deliberately not starting with ordinary homeowners. It is targeting data centers first. The exact same facilities burning through water by the billions of gallons trying to keep artificial intelligence servers cool in the driest regions of the country, along with hospitals and remote industrial sites, where the honest alternative to this machine is not a kitchen faucet. It is a tanker truck driving in on a schedule. Atoko is not working alone in this race either. A separate American company called Waha, operating out of Arizona, is building its own version of an atmospheric harvester, combining chemistry inspired by this same Nobel-winning research with a sealed heat pump engine designed to work reliably in the harshest desert conditions on Earth. As of this past August, Waha reports that it is already producing dozens of complete units every year, with plans to scale into the thousands annually by 2027 and tens of thousands of units per year by the start of the next decade. Separately, engineers at MIT have been chasing a parallel approach using a completely different material, a water-absorbing hydrogel loaded with hygroscopic salts and shaped into small domes that swell and collapse like tiny pieces of origami as they take on and release moisture. Tested in that same brutal Death Valley environment, their hydrogel panel produced between 57 and 161 milliliters of water per day, with a working lifespan of at least a year and extremely low salt contamination in the final water. It is a smaller number than the MOF approach, but it is more evidence that American research institutions are attacking this exact problem from multiple directions at once. It is worth pausing here to remember that not every water from air company survives contact with the real world. Source Global, a company based in Scottsdale, Arizona, spent roughly a decade building an entirely different unrelated approach using solar-powered hydropanels rather than metal organic frameworks. The company raised something in the neighborhood of $270 million across 4 funding rounds between 2014 and 2024, before going largely silent and losing its founder within about 12 months, according to reporting published earlier this year. The difference this time with Atoko and Waha is that the underlying chemistry did not just attract venture capital investors looking for the next big thing. It attracted the Nobel Committee in Stockholm, which is a considerably higher bar to clear. Not everyone in the water industry is convinced this entire category of technology deserves the attention it is getting. Christopher Gasson, a well-known water industry analyst, has argued publicly that atmospheric water harvesting in general is something of a distraction, and that the serious, unglamorous work of fixing water scarcity actually lies in using the water we already pull from rivers and underground aquifers more carefully and with less waste. It is a fair point, and it deserves to be said plainly in this video instead of being ignored. Researchers at Arizona State University, including water treatment specialist Paul Westerhoff, have separately estimated that water produced this way currently costs somewhere around 10 times what most Americans already pay for ordinary tap water, and more than water produced through large-scale ocean desalination plants. Conventional atmospheric water generators, the older style that simply chill air down to its dew point like an air conditioner, typically burn between 0.3 and a full kilowatt-hour of electricity for every single liter of water they produce. The MOF-based approach mostly sidesteps that electricity bill by relying on sunlight instead of a compressor, but it has not yet erased the underlying cost of building and deploying the equipment itself. So if this technology is real, scientifically validated, commercially funded, and now literally Nobel Prize approved, why is there not one of these machines bolted to the side of your own house already? Start with the basic yield. 210 grams of water a day running passively means that a full kilogram of expensive, precisely engineered crystal produces a little less than 1 cup of water every 24 hours. A single adult needs roughly 10 times that amount just for drinking water alone. Scale that requirement up to an entire neighborhood, and you are no longer talking about a small box sitting in a garden. You are talking about literal tons of engineered material, which is exactly why the first working machines are the size of an entire shipping container rather than a kitchen appliance. Then there is the manufacturing bottleneck, which might be the real obstacle hiding behind all of this. The underlying chemistry has been scientifically validated for the better part of a decade now. What has not been solved yet is how to manufacture metal organic frameworks cheaply, safely, and at true industrial scale without relying on the toxic organic solvents commonly used in early laboratory synthesis methods. The chemistry works beautifully in a beaker. The factory capable of repeating that same chemistry a million times over, cheaply, safely, and without an environmental cleanup problem of its own, does not fully exist yet. And underneath both of those obstacles sits one more quieter reason which has almost nothing to do with the science itself. Municipal tap water across most of the United States is priced against pipes, pumps, and treatment plants that were built and paid off decades ago. Nothing brand new can easily compete on price against what is arguably the most heavily subsidized utility service in the average American household. That single economic fact explains more than anything else why Atoko and Waha are not chasing ordinary homeowners as their first customers. They are chasing the customers for whom the real honest alternative is not a kitchen tap at all. It is a scheduled delivery truck. So what can an ordinary person actually do this year while these shipping container machines are being reserved almost entirely by data centers and hospitals? The most useful answer has nothing to do with pulling water from thin air at all. It involves looking up not at the desert sky but at your own roof. 1 millimeter of rainfall landing across 1 square meter of surface delivers exactly 1 liter of water. An average roof measuring about 100 square meters. Sitting in a region that receives around 600 millimeters of rain in a typical year, theoretically intercepts around 60,000 liters of water annually. After realistic losses from gutters overflow and the standard practice of diverting the first dirty flush of rain away from your storage tank, that number settles closer to 45 or 50,000 liters a year in practice. That is somewhere between 100 and 1,000 times more water than any atmospheric harvester on the planet could hand you for the same amount of money, using nothing more advanced than ordinary gutters, a simple leaf filter, a first flush diverter valve, and a storage tank sitting against the side of your house. None of that requires a Nobel Prize winning chemist. All of it is sitting on the shelf of a hardware store within driving distance of wherever you live right now. And if your local climate happens to deliver regular coastal fog instead of steady rainfall, a simple mesh collector stretched across a frame, essentially just fine netting, catching droplets out of passing fog banks, remains one of the cheapest water harvesting technologies that has ever existed, and it is already fully commercial and available today. To be completely honest about where this specific technology actually stands right now, even Atoko itself is not promising a small consumer version for your own backyard this year, and probably not within this entire decade either. The pricing target the company has discussed publicly, aiming for something in the range of just a few cents per liter, is still more expensive than water produced through ocean desalination at scale. This is not a small countertop appliance you plug in next to your refrigerator. It is early-stage industrial infrastructure deliberately built first for the specific places that need it most before it ever makes its way toward the average driveway or backyard. What makes this whole story worth remembering is exactly where it started. An Australian chemist playing with cheap plastic ball and stick models in an ordinary classroom back in 1974, simply wondering out loud, what would happen if the empty gaps between molecules were built on purpose instead of by accident? 51 years later, that one quiet question ended with a phone call from Stockholm, a parking lot outside a laboratory in Irvine, California. And a machine that can turn dry desert air into something clean enough to drink, developed almost entirely inside American universities, and an American company by a scientist who arrived in this country as a 15-year-old with no money and no connections. If you had to choose this year between waiting years for an atmospheric water harvester to reach your price range or simply catching the 45 to 60,000 liters already falling for free on your own roof every single year, which one would you actually put your money on first? Tell me your answer in the comments below. And if stories like this one, ideas that almost got overlooked as laboratory inconveniences before quietly becoming some of the most important American engineering achievements of the entire decade, are exactly the kind of thing you want to keep discovering, go ahead and subscribe. That is the entire reason this channel exists.